Okay, here we go. We're recording. So before we jump into the lecture, a few announcements to make about basically the end game of the class. We're getting pretty close to the end of the class. So what we have coming up is test 3 and the final exam. Let's just do a quick rundown of those two things. You've already taken 2 tests, so you should be pretty used to the format and how things go. So test number 3 is going to be a whole lot like test numbers 1 and 2. It's going to be given during the lecture on Monday, May 2nd. That's when the third test will be. And here's what the test is going to cover. Chapters 11 through 13 of the textbook. Remember, we're using volume 2 of the textbook. So this material is magnetic fields and forces. That's the lecture we just finished on Monday. Then sources of magnetic fields. That's the lecture we're going to start today and finish next week. And then finally, Faraday's law, which we'll just spend 1 week on before the test. Okay? So all that content, that's what's on test 3. Just like before, between 5 and 6 questions. And also just like before, there will be a review packet, which we'll go over in lab the week before the test. And you'll be able to bring a cheat sheet to the test. Remember, that's a half sheet of paper filled out on the front and back with whatever you like. So the test is a ways away. It's almost 3 weeks away. But I want to just put it on your radar, okay? Also, final exam. The final exam, our time slot is actually the very last day of finals week, so it's on Wednesday, May 18th. Now, keep in mind that because we have finals time slots, they're different from our lecture time slot, okay? The final, it is going to be in this room, but the time is going to be 2:15 to 4:45 p.m. That's the time we've been given. Okay, so it's a 2.5 hour block of time. It's longer than the lecture, which means, well, the test is going to be longer. It's a final, right? So what you can expect is between 8 and 10 problems for the final exam. Now, because of the increased length of the exam and the more broad range of content that it's going to cover, the cheat sheet for the final, just use a whole sheet of paper front and back, okay, because you'll need to write a lot more stuff down on that, all right? So there will be a final exam review packet. We will go through that during the very last week of class. So yeah, does that cover everything? Yeah, the final is cumulative, by the way. Everything is fair game for the final. Any questions on that?
And also, we don't have lab next week, right? I think I saw that on Canvas.
Yeah, next week, I'll tell you more about this on Monday of next week, but just a heads up, we won't have lab. Because Wednesday of next week is actually a day off. Okay, so we're actually just going to miss Wednesday entirely. And because of that, I just cancel lab across the board. So we will meet in person for lecture on Monday next week as usual, but no lab. And then for Wednesday, I'm going to pre-record a video and it's going to be on you to watch that. Okay, so there's no lab next week, but there are 2 lectures next week. One of them is in person on Monday. The other I'm going to prepare a video for. And I'll probably just do that sometime early next week. Okay, so you'll have it available to you by Wednesday. All right? Any other questions? All right, so then without further ado, let's get into the new chapter on sources of magnetic fields. This content is coming from chapter 12 of volume 2 of the OpenStax textbook. So a brief overview before we get into it. The previous chapter basically is a discussion of the forces and the torques that magnetic fields can exert on particles or currents that may be carried through a wire. But we haven't yet really discussed where the magnetic fields come from in the first place. That's what this chapter is all about. Understanding the origin of magnetic fields and also how to calculate a magnetic field based on currents. Okay, so that's what we'll get into here. And the first case we'll look at is the magnetic field produced by a long, straight wire. In a lot of ways, this is the simplest magnetic field we'll encounter. So we'll start with it and then build up our understanding from here. So of course, what you should be imagining is just a wire. It has some current flowing through it. The wire is perfectly straight. It's not bent into an arc or twisted up into a coil or anything like that. Just a straight piece of wire with some current running through it. Okay? So, for this one, I'm just going to tell you what the result is, Later on, we'll learn how to derive this, but for now, let's just use this as a result. The magnetic field from a long straight wire, first of all, forms loops around that wire, okay? So you see in this picture, this is a segment of the wire, and the current is going up like this. And we see the magnetic field B forming circular loops around that wire. That's exactly how it goes, okay? So if we want to understand the direction, we just need to understand whether these loops are going this way or the other way, like clockwise or counterclockwise around the wire. For that, we have a right-hand rule. There's another right-hand rule we're about to learn about here, okay? This is how it goes. The right-hand rule to find the direction of B, that's your magnetic field, goes like this. You point the thumb of your right hand in the direction that the current is flowing. That's what you start with. And then your fingers will naturally be curled in the direction of the B field. So you see how this works? If our current is going up the wire like this, thumb goes up like this, fingers curl like this. That's telling me which way the B field loops around the wire. And of course, if the current were going the other way, then the B field would loop in the opposite direction around the wire. Make sense? Okay, so that's how we understand the direction of a B field in this sort of simple case. What about the magnitude? Well, for the magnitude, I'll give you the formula, which we'll understand how to derive later. The magnitude of B at some point nearby the wire, so we'll call this point P, that's where we're calculating the field, is given by mu naught times I divided by 2 pi r. Okay, let's understand all those variables. I, of course, is the current. That's pretty straightforward. R, that's your distance between the point and the wire. And in particular, this is what we call a perpendicular distance. So if you draw a line that runs perpendicular to the wire out to the point, it's the length of that line that defines R, okay? So that's how we talk about your distance to the wire. So it's a 1 over R sort of relationship. That means the closer you are to the wire, the stronger the field is. The further away you are from the wire, the weaker the field is. That should make basic sense, given what we've seen before. Okay, what about this thing, mu naught? This is a new constant. You haven't seen this before. This is something called the permeability of free space. I'll give you the value of it right here. The value of this constant mu naught is 4 pi times 10 to the minus 7. The units are Tesla times meters per amp. Let's discuss what this constant is sort of doing in our equation. Basically, it sets the strength of the magnetic field overall, right? We can imagine if we were to dial this constant up, we would get stronger magnetic fields overall, and if we were to dial it down, we'd get weaker fields. It plays a very similar role in our equations to epsilon naught, if you recall, for electric fields, right? This one just applies to magnetic fields. Okay? Any questions on that?
So the formula we were learning was like the magnetic field was just like straight lines, and like a current of wire was, the wire current was in that like straight line of magnetic field. What's the difference between these ones?
This is, okay, before in the previous lecture, we were purely discussing if there's a magnetic field present, what kind of force will it exert on something, okay? So we already have some magnetic field established. What does it do, right? That's what the previous lecture was about. This lecture is about, okay, what does the magnetic field in the first place actually look like? How can I figure out what the magnetic field created by a current actually is? Okay, that's what we're doing. All right, so I'm going to ask you a few conceptual questions. These just are going to involve you sketching out a picture on your paper, and you should be able to answer it if you get the right sketch. So in this picture, we have 4 wires which carry equal currents, and they're arranged in like a square pattern. So what you should be thinking of is the currents are running like into or out of the page. So for example, up here, this is wire number 1. The current is into the page. Remember, that's our symbol for into the page. Wire number 2, that's also carrying a current into the page like this. 3 and 4, those are carrying currents out of the page, all right? So each one of these is going to contribute some amount of magnetic field, right? So what I want you to do is look at the very center of that square, point P, and figure out what is the total magnetic field. You don't have to put a number to it, right? Just draw all the individual magnetic field vectors, okay? And then just tell me how they add up. Do they add up to something that's pointing up overall? Do they add up to something that's pointing down overall? To the right, to the left, or is it 0? Okay? So draw all of those B field vectors, and just from your picture, you should be able to see how they add together. Okay? So just as an example, right? Remember the right-hand rule? Let's take wire number 3. This is a random example. I point the thumb of my right hand out of the page because that's the direction the current's going in. So for wire number 3, it's creating a B field that loops around this way, right? Wire number 4 is creating a B field that loops around this way. Try to see what that B field is doing right at point P. So just draw a vector right at point P for that B field, okay? So take a few minutes and then we'll discuss. Right, so on your paper you should have B1, B2, B3, B4, right? You should see how they add together. All right, I'm going to ask you to put it to a vote, okay? Even if you don't quite have your answer, if you're not quite sure, we are going to put it to a vote. So who says the net B field is up? Down? How about to the left? To the right? The 0? Some of you voted twice. It's to the left. Yeah. There's too many hands. Yeah, some fraud going on. Okay, so anyway, here's what we do. For each one of these, we understand that the B field forms a loop around that particular wire. Okay? So we just want to see what direction the B field is going at this point. All right, let's do it for wire number 1 with the current going into the page. Okay? It looks like my B field is going down and to the left at point P. Do we agree? Okay. For wire number 2, it looks like I'm going up and to the left like this, right? For wire number 3, looks like I'm going up and to the left like this. Wire number 4, looks like I'm going down and to the left like this. Do we agree? If we were to draw those loops around each wire, that's which way we would see the B field going in each of those cases. Okay. So if we draw it on our picture, again, I'll just sketch out for wire number 1. It's a loop that's centered right on the wire itself. So something like this, right? Can't draw the whole thing, but that's our loop. And since our current is going into the page, by the right-hand rule, this is the direction of our loop. So right at this point, it looks like this is my B1. Okay? So like I was saying before, it's like down and to the left. For my B2, again, imagine a loop going around that wire, and it's circulating this way by the right-hand rule. So this one at the point in question is going like this, which is kind of like up and to the left. We do B3, again, current's coming out of the page, so our loop circulates around the wire this way. So at this point, that's like up and to the left. And then finally, B4, it circulates around the wire this way. So that's another one that's kind of going down and to the left like this, okay? So if we add these all up, hopefully you can just see the net field is to the left. Okay? Clear on that? Good. All right. So let's do another one. 4 currents, but I've switched some of the directions around. Okay, so now number 1, into the page, number 2, out of the page, number 3, out of the page, number 4, into the page. Run through that same game of at point P, at the center, figure out what direction each magnetic field is going in, and that will tell you how they all add together, okay? So take a minute for that one, and then we'll go through it. Yep. Okay. All right, let's put this one to a vote. All right, you have to vote. Who says it's up? Down, left, right? 0? There you go. Yeah, 0. Let's just run through it real quick again. You can never get enough practice using the right-hand rule because it's going to come up a lot. I've copied the picture down. So number 1, that's just like before, right? This current's going into the page, so we know the B field circulates around like this. So at this point, that B field is just like before, going kind of down and to the left. So this is B1. All right, for number 2, the situation has changed a little bit. It looks like for number 2, now the current is coming out of the page. So we point our finger, our thumb of our right hand out of the page, and then our fingers curl in the direction of the B field. So it looks like now it's going down and to the right like this at this point. Make sense? So there's our B2. All right, let's do B3. I think this one's just the same as before. Thumb's coming out of the page like this in the direction of our current. B field loops around that current like this. So at this point, it's kind of going up and to the left. Okay, there's B3. And then finally, we've got B4. That one's going into the page. So thumb into the page, current circulates around like this. if we're up here, that's going up and to the right. Now the thing is, like B1 certainly opposes B4, B2 certainly opposes B3, but they also have equal magnitudes because we're the same distance away from each wire, right? Distances are equal and the currents are equal, okay? So if we have all these four vectors, but they all have the same magnitude, we get perfect cancellation, okay? So the net field is 0, okay? Good on these examples? All right, then let's move on. Yeah?
I don't get it between B3.
B3.
Yeah.
Because remember, the loop that your B field makes is centered on this wire. And it's going basically counterclockwise, right? So you have to imagine a loop that's going like this. At this point, it's pointing this way, okay? It's always pointing tangent to that loop, if you want to think of it that way, all right? Okay, so now what we can do is kind of take a side quest and use that result to calculate the force between two wires, okay? The idea is, if you have two parallel wires, which are both carrying a current, they will exert a force on one another, okay? And it's actually quite similar to how two charges exert a force on one another. So let's get into it. For our example that we'll use to derive the result, we're going to have a wire here, which has current I1 running through it, and another wire over here that has a current I2 running through it, and you can see the currents are parallel. There's some distance between the wires. Let's call that D. So here's how we're going to go about doing it. First, let's find the force that number 1 exerts on number 2. That's what we want to do. In order to do that, we're going to have to figure out what is the magnetic field. Okay? So again, the goal is to find the force that this guy, number 1, is exerting on this guy, number 2. In order to do that, we need to understand the magnetic field that number 1 produces, okay? In other words, number 1 is producing a magnetic field at the location of this wire, and that's what exerts a force on it, okay? We know if there's a magnetic field, it's going to exert a force. So let's find that magnetic field as our starting point. Okay, let's start with the direction, okay? I know that for wire number 1, my current is going up. So if I'm trying to figure out how the magnetic field is directed, I point the finger, the thumb of my right hand upwards, and then the fingers curl in the direction of the B field. So what direction is my B field going? Over here.
Into the page.
It's actually going into the page, right? At this point right here, my fingers will be curling, pointing into the page. Okay? So the direction of B1, according to the right-hand rule, is into the page. So you see, right over here, where the second wire is located, we have a magnetic field produced by the first wire, which is going into the page. All right? Good on that? What's the magnitude of that B field? Well, we have a formula for it, right? It's basically just going to be U naught times the current divided by 2 pi times the distance. But let's just be really clear about what we're doing. We're calculating the magnetic field created by the first wire. So the current that we should put in there is I1. And then I'm calling the distance D. You could call it R, doesn't matter. We're just talking about the distance between them, okay? So I have D1, the magnitude of that field is equal to mu naught times I1 divided by 2 pi times D. Are we good so far on this? All right, so the next step, now that we know what the B field that wire number 2 is immersed in, okay, we can now calculate the force that it's feeling from that B field. So the force on wire number 2 is going to be given by IL cross B. Wire number 2 is inside of a magnetic field. It's inside of the magnetic field produced by wire number 1 in particular. And we know already from the previous chapter how to calculate the force, okay? And that's what we're going to do. It's going to be given by IL cross B. So how about we start with the direction, okay? The direction that one exerts, the direction of the force that one exerts on 2, given this equation here, right? We're just doing the right-hand rule, so let's think about it. We take L, which goes in the direction of the current, okay? And then we cross with B. B is going into the page. The current is going up. So here, let's do it. L goes up. Curl your fingers into the page in the direction of the current. Which direction is the force going?
Negative X.
It's going to the left, all right? So it looks like we have an attractive force, don't we? So that force, F12, remember, that's the force that wire number 1 is exerting on wire number 2, we determined just now is going to the left, okay? Now let's work out the magnitude. Well, the current that goes in this formula is now I2, because that's the wire we want to calculate the force on, okay? The length is whatever the length of that second wire is, I'll call that L2. But the B field is the one that's created by wire number 1, that's labeled B1, okay? What's the angle between the current here and the B field? It's actually 90 degrees, right? This one's going straight up, this one's going into the page, 90 degrees. And we can plug in this for B right here, okay? So let's put it all together, right? Sine of 90, that goes to 1. B is going to be this expression up here. So overall, here's what we have. We have mu naught times I1 times I2 times L2 divided by 2 pi d. Okay? And let's also take note of the fact that we found the force that 1 exerts on 2. There should also be a force that 2 exerts on 1. Does anyone know how to think about that? Think back to Newton's third law, way back in physics 44.
It's negative, right?
Yep. It's an equal but opposite force, right? If 1 is pulling on 2 this way, 2 must be pulling back on 1 in the other direction with the same amount of force. That's basically the third law, if you recall, okay? So by Newton's third law, wire number 2 exerts an equal and opposite force on wire number 1. So I'm calling that force up here F21. So what's the takeaway? We've got 2 parallel wires. They've got currents going in the same direction. They attract each other. They attract each other with a force that we just derived right up here. Okay? So this can be used to calculate that force.
So L2 wouldn't change to L1? Like if they were the same length? If they were different lengths?
So yeah, we're going to do the generalization of this, but it's the best way to think about it is like force per unit length. And then you can plug in whatever relevant length is there. Yeah.
So before we were just working on like again a wire and a magnetic field. This whole time like wires have their own magnetic field.
Yep. It's just, but it's no different than what we encountered with charges, right? If you put a charge inside of an electric field, that feels a force, correct? But a charge itself also produces its own electric field. It's really the same thing with magnetic fields. Yeah. Okay. And then there's also just one rule to remember. A charge or a current or whatever can't exert a force on itself, okay? That's why when I wanted to figure out the force on wire number 2, it's the B field from wire number 1 that's exerting the force. It doesn't exert a force on itself, right? That's why we did it. Okay, Pierre?
Yes, Professor, why do you use the force the wire 1 and 2, you use I2?
Because, remember, what this formula means in the first place is it's the force acting on a wire that has a certain current. We're trying to find the force on this wire, which has current I2 running through it. So that's why. But at the end of the day, the force depends on both currents. So there's a symmetry in it, okay? So let me show you a more general way of thinking about that result we derived, okay? We have two parallel wires. There are two basic cases we can see. One involves the currents going in the same exact direction. That's the one we did. So when we have the currents going in the same direction, like this, the force ends up being attractive, right? The wires are feeling a force that attracts them towards each other, okay? That's the case we just did. We're not going to go through the entire process all over again, but if you sort of switch things around so that now the currents are in opposite directions, what you'll find is now the wires repel each other, okay? So currents going the same way, the wires attract. Currents going opposite directions, they repel, all right? And in either case, we can think of the force per unit length. Now, this is the same result I derived before, except basically instead of having the L on top over here, I'm dividing it out so the L is on the bottom over here. This is a more standard way to write this result, is that the force per unit length is equal to mu naught times I1 times I2 divided by 2 pi d. Okay? This is the force of attraction or repulsion between two parallel wires. That's how it goes. All right? Any questions on that? So let's do a few examples now where we use the result. Here's one that I want you to work out, okay? So let's say we have an extension cord, and basically keep in mind that when you hook up an extension cord to your wall outlet, there are two wires inside that extension cord, right? One is carrying a current going towards your device, the other is carrying what's called the return current coming back into the wall, okay? So an extension cord has those two wires. So let's say that for this particular extension cord, the wires are separated by 3 millimeters, so 3 millimeters between them, okay? Each wire has a length of 2 meters, and basically the wire on the top carries current from our power source to this light bulb, and the other carries the current coming back to the power source. Let's say the power source is 32 volts. You can imagine this is a battery, if you like, it doesn't really matter, some kind of DC power source. Okay, let's say the resistance of the bulb is 4 ohms, and the resistance in the wires is pretty much negligible, okay? My question for you is, what is the magnitude of the force between these two wires? And then, is it attractive or repulsive, okay? So use this equation we derived. The first thing you're going to have to do is calculate what the current is. That should be pretty straightforward. Just remember Ohm's law. Get the current, plug that into here along with everything else you know, and you should be able to tell me what the force is. All right? So take a few minutes to do that, then we'll go through it. don't have to put like a sign in for I, but what you should do is realize what that means they would cut. So that the I values are actually the same.
Yeah.
23. All right, let's answer the second part first. Is this attractive or repulsive? It's repulsive, right? We just saw that result. Currents going the same way in parallel wires attract, currents going opposite ways in parallel wires repel. So it's a repulsive force. Now let's figure out how much force there is. By the way, if it's a really huge repulsive force, you might worry it rips the cord apart, right? But as it turns out, it's a really small and insignificant amount of force. That's not really a problem for us, okay? So how about we start by figuring out what the current is, okay? So yeah, first of all, let me just write down the answer. It's repulsive force. All right, now let's figure out what the current is. Let's just use V equals IR. It's really that simple because you just have a voltage source hooked up to a resistor and no resistance in the connecting wires, right? So it's really just this simple. So the current should be the voltage of our source divided by R. So that would be 32 volts. That should be a 3. Let's start with 32 volts divided by 4 ohms. And remember, an ohm is a volt per amp, so this comes out in amps. Comes out to a nice round number of 8 amps, right? So that's how much current we have actually in both wires, right? Because you just have a single loop of the circuit, there's the same current everywhere. So both I1 and I2 are 8 amps. So keep in mind this is for both. All right, cool. So then let's calculate F. If you recall, F is given by mu naught times I1 times I2 times L. Let's just put the L on top over here. Divided by 2 pi d. And let's put in the known values. Okay. Mu naught, I gave you that value before, so hopefully you wrote it down. This constant is equal to 4 pi times 10 to the minus 7. And it has kind of a weird unit, which is Tesla times meters per amp. All right, now we have two currents, which both are 8 amps. So I1 and I2 both get a value of 8 amps. The length, that was 2 meters. All right, divide this out. We have 2 pi, and then the distance between the wires, that was our 3 millimeters. So let's say 3 times 10 to the minus 3 meters, okay? Now, I'm not going to go through the whole unit analysis here. Again, what I advise you to do when the units get complicated is just put everything into your equation with SI units. What comes out should also have SI units, all right? What's our SI unit of force? So I'm expecting some number of newtons. And what is that number? Yeah, it comes out to like 8.5 10 to the minus 3 newtons, which is not a very significant amount of force, right? So you're not in danger of destroying the extension cord with this force, not at all. Okay? Any questions on that?
Go for it.
Is that the force that one wire exerts on the other, and then does the other one have?
Yep. Yeah. They're exerting this same exact amount of force on each other. That's the third law in action, right? They're, they're each repelling each other with this amount of force. Okay, it's a mutual force, mutual repulsion. Go ahead.
Yes, so let's say you have this question on the test, and you were not state that the wires do not have the resistance. And you have to just assume that you don't understand?
Yeah, so what, and again, this came up like way back, so I just want to remind you. When we do problems, if the resistance in connecting wires is not mentioned, you can just assume it's 0, but some problems say, okay, let's not assume it's 0, let's work with it, and those are a separate type of problem, okay? So yeah, one example of that would be like the test that we have. All right, let's do another one like this. So now what we have is a long horizontal wire that has current I1, 80 amps running through it. We have a second horizontal wire which is placed a distance of 20 centimeters directly below it. This wire, the one that's sitting below it, has a mass per unit length of 0.12 grams per meter. That just means for every meter length of the wire, the mass of it is 0.12 grams, okay? That's what we have. What current should run through it? What should this current I2 be in order for it to be suspended in the air? And as a follow-up, what direction should the current flow? So let's think about this for a second, right? We know that in this kind of situation, two wires can either attract or repel each other, okay? But we're imagining that there is a downward force of gravity acting on this wire. So normally it would just fall to the ground, but it isn't because there's a magnetic force provided by this top wire, which is attracting it, okay? So the picture you should have in your mind is gravity goes down, magnetic force goes up, and overall they're in balance with each other. That's what allows it to be suspended in the air. So we need an attractive force. What direction should the current be going? Yeah, the current should be going in the same direction as I1. That way we get an attraction. If it were repulsive, that wouldn't help us, right? So currents are going in the same direction. All right, so now that we've established that, let's do the calculation. How much current is necessary? There's a specific value that's going to make it work out, okay? So the force must be attractive, as we've determined. So here's the picture. The top wire has current I1. The bottom wire has current I2, which is going in the same direction, which means the magnetic force, I'm going to call this F12, that's the force that wire number 1 is exerting on wire number 2, is attractive. And then of course we have our downward force of gravity, Fg. Okay? Now what we can do for wire number 2 is apply F equals ma. Let's do it in the y direction for wire number 2. So we have two forces, right? We have going up, F12, and then going down we have Fg. So the sum of the forces is just F12 minus Fg, right? What's the acceleration? 0, right? We're assuming it's suspended, so there's no acceleration. All right then, so that just means F12 equals Fg. This has to exactly equal the force of gravity to suspend it in the air, right? Pretty straightforward. So let's come up with a formula for both of these things. So for F12, that's our result derived previously, which says mu naught I1, I2 times the length, which I'll just call L, whatever this length is, divided by 2 pi d. Now that's going to equal gravity mg. Remember, I'm trying to find I2. That's my goal. So let's just shuffle the terms around so that we can solve for I2. So looks like the first thing I could do is multiply 2 pi d to put it on top. And I can divide out mu naught I1 and L. Okay? But what I'm going to do is for the L, instead of putting it down here, I'm going to group it together with my mass. So I'm going to just write this as m over L on top. The reason for that is we're given this exact quantity, which is mass per unit length, so it's just a little easier to group it up here, okay? And then lastly, we have G on top. I think that takes care of all our terms. So hopefully that's pretty straightforward. Let's put the numbers in. The current I2 is going to be 2 pi times the distance between the wires. That was 20 centimeters, or 20 10 to the minus 2 meters in this particular problem, okay? Okay, the mass per unit length of our wire, that's just m over L right there. That was 0.12 grams per meter. We want that to be in kilograms. So 0.12 grams is the same as 0.12 10 to the minus 3 kilograms, and again, that's per meter. That's the mass per unit length, all right? Then we have G, that's 9.8 meters per second squared. Then on the bottom, we have this constant mu naught, 4 pi, 10 to the minus 7, basically TMA, Tesla times meters per amp. And then we have I1, that was our 80 amps of current. All right, kind of a lot going on there, but if we do the calculation, we'll get current I2, and can someone tell me what it works out to?
Uh, 14.7.
Yeah, something like 14.7 amps. And then we determined it goes to the right. Okay, that's what would be needed. So hopefully that's pretty straightforward. Okay. Any questions on this one? Right. So we're about to move on to a new topic. Before that, I will talk a little bit more about this mu naught constant. But what we're about to get into next, and basically for the rest of this lecture, is how to calculate a magnetic field in general. Okay? This is going to look pretty reminiscent of some stuff you saw way early in the semester. Remember calculating E fields with Coulomb's law and Gauss's law? There's a pretty much mirror image of that stuff when it comes to magnetic fields. Okay, we're going to get into that today. Okay. So yeah, before that, just a kind of quick sort of historical note, I guess, about how we define some of our common units. The ampere for current and the coulomb for charge, okay? So the way we define units is actually constantly shifting. We always come up with more and more accurate ways to do these sorts of things. The current standard is this. The permeability of free space, this constant, which we call mu naught, you may be looking at it and wondering, like, why is it 4 pi 10 to the minus 7? It's like a weird coincidence that it worked out to that exact value. It's actually not a coincidence at all. It's just defined to be that value, okay? We just sort of declare mu naught is 4 pi 10 to the minus 7 Tesla times meters per amp. That's just by definition. Then once we have that definition in hand, other units can be defined, okay? So for example, if this is what mu naught is, that defines what the ampere is. So the definition of an ampere is this is how much current would be flowing through two different wires parallel to each other if they're separated by 1 meter, such that the force per unit length between them is 2 times 10 to the minus 7 newtons per meter. So it's basically how much current you have to run through two wires, which are separated by a certain distance, to get a certain force, okay? That's how the ampere is defined, okay? Once we have the ampere, we can then define the coulomb. It turns out it's a lot easier to measure currents than charges. It's hard to kind of like store a bunch of charge on an object and measure exactly how much you have. Much easier to measure a current. So if we define the ampere as a unit of current like this, the coulomb as a unit of charge is just an ampere times a second, right? Because an ampere is a coulomb per second. So if we know what an ampere is and we know what a second is, we automatically get the coolant for free, right? Okay, and what these are examples of operational definitions for our units, right? Whenever we have a certain unit that we use to measure a quantity, you want a way that you can easily reproduce that measurement in the laboratory, right? And this allows you to do that, okay? So anyway, that's the side note. If you're ready, we can get into something called Ampere's law, okay? So this is kind of the mirror image of Gauss's law. You guys remember Gauss's law? Okay. If you're comfortable with Gauss's law, then it shouldn't be too much of a stretch to understand Ampere's law, okay? So we'll get into it. Let's start off by discussing the idea behind Ampere's law, okay? It's one thing to use the law to make calculations, but before we even go there, I want to make sure you understand what the law is telling you, okay? What's the idea behind it? So we'll start with this picture right here, and then we'll do some work on paper to get the actual result. So what are you seeing in this picture? You're seeing a current, okay? The current is right here. Imagine there's a wire coming out of the page like this. The current is coming out of the page towards you guys, okay? We know what the B field looks like in a situation like this. We know it's given by the right-hand rule. So thumb in the direction of the current, your fingers end up curling in the direction of the B field like this. So it looks like it's going counterclockwise, right? So your B field lines are just loops that go around the current. That's shown in red, okay? That's just what the B field looks like. What I want us to consider is what it will look like when we integrate over that B field, okay? I want you to consider the integral B dot dl. You should know how to do this kind of thing already, because previously we've done the integral E dot dl to get a voltage or a potential difference, right? So all we're doing is we're taking basically some kind of path that traverses the B field and integrating over that path. And do you remember what this symbol means? It's not just a normal integral. It means we have a closed path, okay? That means the path starts at one point and then it comes back around and ends at that same point, okay? So we're talking about closed paths, okay? Right, two examples of closed paths are path 1 and path 2. All right, they're both closed because they both loop around and form a closed loop. But can you see how they're a little different? You see, path 1 doesn't enclose any current. There's no current inside of this path. You see that? The current is all outside of that path. Path number 2, that is enclosing some current. Basically, the entire current in this problem, or in this picture, is enclosed by path number 1. Turns out, there is a difference in how the integral comes out for these two, okay? What I'm going to show you is that if we integrate over a path that does not enclose any current, then B dot dl always comes out to 0. If we integrate over a path that does enclose some current, then B dot dl comes out to something that involves what that current is, okay? So therefore, we can relate the B field to the current that you're enclosing, and we can use that fact to calculate what the B field actually is, okay? All right, so let's do a little work to show that. Don't just take my word for it. So I'm going to set up a similar kind of picture where we have a long straight wire and the current carried by that wire is out of the page. So far it's just the same situation we had. So here's our current I coming out of the page. I'm just going to draw one of those B field loops. You could draw a whole bunch of them, but I think it's enough just to show how one of them is going. That's as good as I can do, so work with that. All right, and as we know, the B field in this case is going counterclockwise, okay? So, check this out. I am going to draw a closed path which will integrate the B field over, okay? I'm going to start that path right here, and then eventually I'm going to come right back around to that point, okay? All right, first part of my path is going to go like this. So basically, I'm going to make half of a turn. We start just above the wire. We're going to do like a half circle, end up just below the wire like this, okay? Let's call that number 1. All right, now we're just going to go a little farther out from the wire, directly away from it like this. Let's call that segment number 2 of my path. Next, I'm going to go all the way back to the top of the wire in a much bigger loop, like this. Okay, that's going to be number 3. And then I'm going to end this by going straight down back to the point where we started, okay? And that is going to be number 4. Okay, so 1, 2, 3, 4, giving us a closed loop, okay? All right, so can you guys tell me how much current are we enclosing? We're enclosing nothing. We're specifically like avoiding the currents deliberately, right? So there's no current enclosed by this loop that we just drew. Okay, let's do the work of integral b dot dl for the entire loop, okay? So this is how it will go. We're going to break it up into the 4 pieces that I just mentioned. So this will be like b dot dl1 plus b dot dl2, both integrated over their respective paths, plus b dot dl3, and then b dot dl4, right? That's just saying do this integral for all 4 parts. Okay, and we're going to look at all 4 parts individually. And I think it may help for the B field. That's the solid line, by the way. The dashed line is our path. The solid line is the B field. I'm just going to show a few more arrows on the B field line so you can see which way it's going. Okay? All right, so let's do B dot DL 1. Okay, now first of all, our DL, our sort of little piece of the path, is going down. See that for segment number 1? Whereas the B field is going up. So when we take the dot product, remember this is the same as saying B times DL1 magnitudes times cosine of some kind of angle, right? What would the angle be for path number 1 between my path and my B field?
180.
That's 180. See, they're directly opposing each other, right? All right, what is cosine 180?
-1.
It's -1. So overall, this introduces a negative sign. The nice thing about this path is that it's circular. So we're always the same distance away from the wire. See, B only gets stronger or weaker if you change your distance from the wire. But we're not doing that here. We're staying the same distance away. That means B, the strength of the B field, can be pulled out of the integral. It's the same over the entire path. So now we just have minus B pulled out of the integral times integral DL1. Okay. Well, when we integrate over DL, we're just essentially getting the total length of the path, right? What kind of total length should we be dealing with for path number 1?
Half circle.
It's a half circle, right? So here, we'll have minus I'm gonna sub something in for B, but let's show how the integral dl works out. I know if I have a full circle, the total distance around that is 2 pi r. So if I have half a circle, pi r, right? Pi r. And actually, I'm going to say r1 because that's the radius of this path. r3, this bigger circle, is going to be something else. So I just want to be specific here, okay? What can we put in for the B field? Well, that's mu naught times I divided by 2 pi r1. We're just going to take this result as given. We went over this at the very beginning, right? We good so far? This is B. This is the total length of the path. There's a negative sign there. That's important. Okay, so pi and r1 go away. We just have minus 1/2 mu naught times I, don't we? We agree? Let's do number 2. Let's do b dot dl2. This one's a little simpler. Can anyone see what b dot dl2 is going to end up being? I think I heard 0. Why is that? It's correct, but why?
Cosine is equal to 90, right?
Yeah,
Cool. Cosine.
your path is going exactly perpendicular to your B field for number 2, okay? And when that's the case, the dot product ends up being 0, right? Because we have B dl2 cosine, there's a 90-degree angle between them. That just works out to 0, right? All right, let's do it for number 3. We've got b dot dl 3. All right. Now, let's start by thinking about the angle. What's the angle between my B field and my path for number 3?
180.
It's 0. They're going the same way this time, okay? For path number 1, it was directly opposing the B field, but now it's going directly with the B field, okay? So what we have is b dl3 cosine 0, which gives us a factor of 1. Also, just like before, because this is a circular path, we're always the same distance away from the wire. Means the B field is the same strength everywhere along this path. That's why you can pull it out of the integral, okay? So we have b dl3 in the integral. Now this works just the same way as before, right? I know the B field is given by mu naught times I divided by 2 pi times r. Let's use r3 because we're talking about whatever this radius is. And then for the integral dl, that's the total length of that path, and that's half a circle once again, right? Half a circle is pi times r, and in particular, we're talking about this radius 3, okay? So just like before, pi r factors cancel. This one gives you positive 1/2 mu naught times I. All right? Now let's do the last one, b dot dl4. What's that coming out to? Yeah, this is another case where our path goes perpendicular to the B field. So that's going to be b dl4 cosine 90 between them. You see that? That gives you 0. So what's the total integral b dot dl over the closed path? That's going to be minus 1/2 mu naught I plus 0 plus 1/2 mu naught I plus 0 gives us a total of 0. Basically, these two contributions cancel. So what do we find? If you enclose no current with your path, v dot dl around that path guaranteed to be 0. Okay? Go ahead.
This is for any kind of path, right? It's just a whole page.
Yeah, so again, I have to illustrate this with a specific example, but this does generally hold true. Okay? Now let's consider a path that does enclose current. Now don't worry, we're not gonna have to do it all from scratch. I can very easily take what I started with and turn it into a path that does enclose current. How can I do that?
Move the current or no?
I'm not allowed to move the current. I can move my path though. So how about we take path 1 and we just flip it over to the other side. You see that? If I put path 1 on the left side, then I'm enclosing the current now, okay?
What if you join 4 and 2? Like, what if it went like right on top of it? Would that be like?
So depending if the current is like, let's say in a wire, then you might be splitting the wire in half and you can close half of it. But let's enclose the whole thing. All right, so we all have this picture now. I'm gonna modify it. I'm gonna say, forget that. Let's now do this. So all of the work that we have for path 2, 3, and 4, that's the same. We don't have to do it again, right? It's just path 1 that's changed. Now what happens with path 1? We have b.dl1. Can anyone see how that's going to work out this time? See, this is my new path 1. Is it going with the B field or against the B field? Now it's going with the B field, right? Now the angle in question, so we have B times dl1 cosine 0. Before we had a cosine 180 bringing out this negative sign, okay? Now it's positive. But otherwise the work from before holds, right? So here's what I'm going to say. I'm going to say dot, 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 because you know what to do next. Positive 1/2 mu naught I. All right? So now that we are enclosing this current, B dot dl over the entire path is going to be, well, now I have 1/2 mu naught I plus 0 plus 1/2 mu naught I plus 0, which is mu naught times I. Okay? That's Ampere's law right there. B dot dl equals mu naught I. That is what Ampere's law says. Okay? So we just derived it. Any questions?
Yes, Professor, I agree with the calculation, but I don't understand how do we enclose the current? Because what we did now is just going to do the same time. I can't see the close part.
So here, let's just draw it on paper, right? So before, original path was like this. Start here, go around, go down, go up, and back down. Now what we're saying is, we're going this way first. See, path number 1 is now going this way, down, around like this. So we are enclosing the current in the second case, okay? In the first case, we avoided enclosing it. In the second case, we were enclosing it, okay? You see that? So yeah, but if you look at this dashed line, it's surrounding the current. That's what we need.
And so you said we can't partially enclose it though, right? It has to be fully enclosed?
No, you can. I'm just doing this for an example. You'll see examples where we have like partially enclosed currents. Yeah. All right. So here's the takeaway right here. Ampere's law says B dot dl over a closed path. This only works if you use a closed path. Equals mu naught times I enclosed. All right? So the situation is basically this. You have some kind of current, right? I'm just showing you a simple case where the current is in a straight wire, but again, we'll see other cases other than just this straight wire case. So what we do is we choose some kind of path. We call this the Amperian loop. The path that we use to do the integral is called the Amperian loop. It's kind of like Gaussian surface, if you remember, right? It's some kind of imaginary loop that we construct in order to solve the problem, okay? So if we take the integral of the magnetic field around that closed Amperian loop, that's the B dot dl part, that's going to equal mu naught, which is this constant we just encountered, 4 pi 10 to the minus 7 TMA, times the total current that's enclosed by that surface, okay? So to be a little bit more precise, right, we have our loop, okay? The loop itself defines like a surface, right? So in other words, we have like a circular sheet inside of our loop, right? I enclosed is the current that's going through that surface defined by the loop. Okay, so if we draw the circle around it, we can see that there's some current like piercing through that circle, right? That's what it means to have an enclosed current, okay? And in a practical sense, what this gives you is a mathematical relation between the B field, okay, that's on the left side of the equation, and the currents that are creating that B field. Remember what we said. B fields are created by moving charges. They're created by currents. And so this gives you a way of relating the currents to the B fields that they are producing, okay? So yeah, Ampere, that's this guy, some French guy, okay. Let's do an example. So what you see in this diagram are 6 different wires. Let's say this wire has a current coming out of the page. This wire, current out of the page, same here. These 3 have currents going into the page. I'm drawing onto this picture 4 different loops, 4 different like Amperian loops. We have loop A that just kind of goes around the whole thing. Loop B goes like this. Loop C is like this. And then loop D is like this, okay? What I want you to do is just rank these in terms of the integral B dot dl. So which one of them has the largest value for this integral? Which one has the smallest value? And what's the order, okay?
That value would be the magnetic field, right? That value, that would be
Well, it's not that, it's the integral. But remember, it's equal, it's just about the current we're enclosing, right? Just look at the picture to determine how much current we're enclosing in each case. The ones that enclose the most current should have the largest value of this integral, okay? By the way, if currents oppose each other, you have to subtract them, okay? Currents go the same way, you add them. Let's do the ranking. So which one of these, A, B, and C, has the largest value?
C.
Okay, and then what's next? Okay, and then? Yeah,
Yes.
you got it. So here, find the current enclosed by each path. That's what we'll start with. If we do path A, we have 3 currents, which we'll just call I, coming out of the page. But we also have 3 going into the page. We are enclosing all of those. So the total enclosed is 3I minus 3I. Actually, that works out to effectively enclosing 0 current, okay? So when we think about enclosed current, opposing currents cancel, okay? For B, the enclosed current, if we think about it, we have 2 that are coming out of the page, 1 going into the page. So that's 2I minus I, the total is I, right? For C, we're enclosing two currents that are coming out of the page, so that's just 2I, they're in the same direction. And then for D, we're enclosing one current coming out of the page and one going into the page. So that's I minus I, that's 0. So because the integral b dot dl is just mu naught times I enclosed, we can rank them in terms of their I enclosed, and that ranking is CB, and then A and D are equal at 0. Okay? Pretty straightforward, hopefully? Okay, let's keep moving then. Okay, so let's now talk about how to apply Ampere's law. In particular, if we're trying to use Ampere's law to calculate a B field, how do we go about doing that? It's very similar to the situation with Gauss's law. Remember how with Gauss's law, yes, we can use it to calculate an electric field, but only if we have a certain type of symmetry that we can exploit. Remember, we had spherical symmetry, we had planar symmetry, we had cylindrical symmetry. When it comes to B fields, the types of symmetry we can use are different, because B fields are a bit different from E fields, but the same basic idea holds true. We can only use Ampere's law to calculate a B field if there's some kind of symmetry to exploit. The reason for that, of course, is if you look at Ampere's law, B is inside of an integral. If you're trying to calculate B, you need to be able to pull it out of that integral in some fashion, okay? That's only going to be possible in certain special cases. So, there are 4 types of symmetry that we're going to study. The first one is a straight wire, okay? Now, for the symmetry to be exact, we need to imagine the wire is actually infinitely long, carrying some kind of current, okay? The next case that we'll look at, we'll just stick to this one for today, by the way. We're not going to get into these other examples until next week. But what we'll see is there's something called a solenoid. This is also known as an inductor if you build circuits. Basically what this is a wire that's wrapped many, many times around a cylinder. Okay? That has a certain symmetry we can exploit. We also have a toroid. Okay? So a donut shape, which has a wire that has a current going through it, wrapped many times around that donut shape. Okay? And then the last one is just a sheet of current. Imagine an infinite sheet which carries some kind of current across it in some direction. All right? These are the 4 cases that we'll study. And we'll start with the wires. This is the one we'll see the most. Okay? So, let's do the first, probably the simplest example of this, which is, let's say we have an infinitely long wire that's very, very thin. And all we're trying to do is calculate the B field produced by that wire. Okay, so the first thing we can take note of is that the B field forms loops, circular loops around that wire. And let's just say for the sake of setting up the problem that our current is going up the wire from our perspective here. So if I want to understand the B field, in which direction it's going, I'll take the thumb on my right hand pointed up, and then my fingers on my right hand will curl in the direction that the B field loops are going. So that's where this picture comes from. Okay? So now we're applying Ampere's law. We have to come up with some kind of Amperian loop. Okay? Anytime you're dealing with a wire, just a long segment of wire that carries a current, your Amperian loop is going to be this. It's just going to be a circle that is directly centered on the wire. Okay? So there's our Amperian loop. It's a circle, radius little r. By the way, we're going to use little r to define that radius as opposed to big R, which will be something else later. Yeah, so there it is. And you can see that the current is going through the surface that's defined by our loop. So we're definitely enclosing some current, right? the first thing we want to do in Ampere's law is figure out what the enclosed current is. In this case, it's totally trivial, right? We're enclosing every single bit of current that's in the wire, right? So our I enclosed is just I. It's just whatever current is flowing through that wire. Other problems where we don't have like a really thin wire, we have to actually figure out what's going on inside the wire. It's going to be more complicated than this, but for now, I enclosed is just the current in the wire. Okay. So now we're going to apply Ampere's law. That says the integral of B dot dl over the closed loop is equal to mu naught times I enclosed. That's the current enclosed by the loop. So basically, what we typically do is we have an I enclosed thing to work out, and we have a B dot dl thing to work out. It's good to sort of work them out separately, then put them back together at the end. That's a good strategy. We did something similar with Gauss's law, if you remember, right? We had our E dot dA integral, then we had our Q enclosed, kind of work them out separately, then put them back together at the end. That's how we'll generally approach this stuff, okay? All right, so B dot dl, let's break it down. That's magnitude B times magnitude dl times cosine of the angle between them. So here, our dl vector is just going basically tangent to the circle, and so is our B field. So B and dl point the same way at every single point along the path. That's why we say we have 0 degrees between them. That's where the cosine 0 comes in, which gives you just 1, of course, right? Okay, the next move we make is to pull B out of the integral. We always want to be able to do this at some point if we're applying Ampere's law in this sort of way. And the reason we can do it is that we're just some fixed distance away from the wire, right? The strength of the B field just depends on how far you are from the wire. So if we're staying the same distance away, the strength of the B field is not changing as we go around the loop. When something's not changing, it's constant, you can pull it out of the integral, right? So we're just left with integral dl. Remember, if we integrate over all the little bits of distance along the path, we just get the full distance of our path. And what is that?
Circle 2 pi.
Yeah, so it's a full circle now, 2 pi r. Yeah? So we have B times 2 pi r, that's the circumference, that's the total distance around the loop, equals mu naught times I. And what does that give us? It gives us this. B, the magnitude of that B field, is mu naught I divided by 2 pi r. And that's a result we already saw, okay? So that's how we get to it using Ampere's law. So one thing to remember when you're dealing with wires is just how the field is oriented, okay? The field is going to form loops around the center of your wire, okay? And then you can just work the rest out from Ampere's law. Any questions on that one? We'll keep going then. So let's actually use that result to make a calculation. The calculation is this. Let's say you had a long straight wire. How much current would you have to run through that in order to get a magnetic field with the strength of 1 Tesla at a distance of 1 meter from the wire? Okay, so in other words, V is going to be 1 Tesla, R is going to be 1 meter. What would I have to be? And then tell me if you think your number is realistic. Okay? So work it out, see what you get.
$5 million.
Yeah. Anyone else get something similar? 5 million amps. Is that realistic? if you would, what would happen if you ran 5 million amps of current through just a normal wire?
Super spicy.
It would get, yeah, I like that. That would get super spicy. Yeah, it would melt. It'd be destroyed instantly, right? So that's not happening, obviously, right? So here, let's do the calculation. We have B equals mu naught I divided by 2 pi r. That means R is equal to 2 pi times B divided by mu naught times I. Let's put the numbers in. We had,
We're looking at I, right?
oh, I'm sorry. Yeah, we're finding I. Yep, sorry about that. Yeah, R is down here. I is up here. Is that right?
Yeah.
No, that's not right at all. Okay. Third time's the charm, guys. All right. I equals 2 pi r times b divided by mu naught. Okay. I always screw up the dumbest things. Okay. There we go. So let's do it. 2 pi r is 1 meter. B is 1 Tesla. And mu naught is a very small number, which makes our result very big. It's 4 pi 10 to the minus 7 Tesla meters per amp, like this. Okay, finally got it right. That's 5 times 10 to the positive 6, sorry, amps. Like you said, 5 million amps. Not realistic. So, why is it then that we can not only produce magnetic fields with the strength of 1 Tesla, but we can do a lot better than that? We can get 20 Tesla or more in a laboratory.
More wires?
Further radius?
More what? Yeah. So there's a number of things we can do. Okay. You're not going to get the strongest possible field just by running current through a straight wire. Instead, if you take that wire and you wrap it up very tightly into a coil, that will give you a much stronger field, as we're going to find out later. Okay? So you kind of amplify the effect of each turn of wire just by wrapping it up into a tight coil. Okay? Also, we can use magnetic materials like iron cores inside of that coil of wire, which will amplify the field. Okay? So obviously, yeah, we don't get the strongest fields just by running stupid amounts of current through a straight wire. We have to use other things to our advantage. Okay? So I'll show you an example here. So this one is a bit different from the first one we did with just a thin straight wire. Here, we're going to imagine a wire that has some kind of thickness to it. And we not only want to understand what the field outside of the wire is, but also what's going on the inside of the wire. Okay? So here we have an infinitely long conducting wire of radius capital R. So capital R is the radius of the wire itself. It is carrying a total current of I, but see, the thing is that current is spread out over the cross-sectional area of the wire. Okay? In other words, it has a current density, which we'll assume here to be uniform. Okay? You guys remember current density? That's coming back. Current density is current per unit area flowing through a cross-section of the wire. We're assuming that that current density is uniform. So based on that, we're going to use Ampere's law to find an expression for the magnetic field as a function of distance from the center of the wire. We're going to have to break this up into 2 parts, okay? There's one expression we'll get when we're inside of the wire, and another expression we'll get when we're on the outside of the wire. Again, if you think back to Gauss's law, this sort of situation should seem kind of familiar, okay? So first, let's apply Ampere's law to loop number 1, where the radius of this loop, lowercase r, is smaller than the radius of our wire, which is uppercase R. Okay? So we're inside the wire, in other words. That's loop number 1. Let's work it out on paper, what the B field is. Okay? So I'm going to draw this picture from a kind of a different perspective, okay? Let's take the perspective of looking like down the barrel of the wire. So we're looking directly into it, like this. And let's say current is out of the page. So the current from this perspective is coming right at us, okay? Now, we know what the B field looks like. It's going to form loops around the center of the wire. And by the right-hand rule, if the current's coming out of the page, that current should be flowing counterclockwise, okay? Or sorry, that B field should be going counterclockwise, okay? So I'm going to draw just one of those B field loops like this. Okay, there's B. And then with the dashed line, I'm going to draw our loop, okay? So the dashed line is the Amperian loop. And solid line, that's our B field. Okay, so hopefully that's clear enough. Not the best drawing I've ever done, but you see what's going on here, right? Okay. So let's actually work out what is the integral b dot dl over that loop. Okay, and by the way, I'm going to label two radii here. Remember, little r is for our loop, and big R is for the actual wire itself. Okay, so we want to keep those straight in our head. All right, so integral b dot dl. That's integral of the magnitude of b times the magnitude of dl times cosine of the angle between them. But if you notice, I've chosen my loop so that it's going in the exact same direction as the B field, right? They're both going counterclockwise. So what's the angle between them here? 0 degrees, correct? Okay, what's cosine 0? It's 1. Next, B is a constant over my loop. It's only a function of distance from the center. And since we're staying the same distance from the center all over the loop, B is a constant as far as we're concerned. Okay? Pull it out, and then we have our integral over dl. Now, what does that work out to? That's just 2 pi r, right? If we integrate over the entire distance around the loop, that's our circumference. So this is B times 2 pi r. We're going to see that whenever we have this type of symmetry, that the integral b dot dl works out to b times 2 pi r. Because we're just integrating over a circle that goes around your current. Okay? Make sense?
And the R is what you use for the Amperian loop, correct?
Yep. That's our Amperian loop, because we're integrating specifically over that loop. Okay? So next, let's figure out the enclosed current. So for this, let's use the fact that the current density is uniform. Okay, what that means is basically J, which is current per unit area, is the same everywhere, okay? So just as much current density in the middle of the wire as on the outside as anywhere else, okay? So that means we can do the following. We can say the current density is just the current we're enclosing divided by the area we're enclosing. So what you should be imagining there is the current just contained within my Amperian loop divided by the area of just my Amperian loop. I should get the same result as if I did I total, which is the total current, divided by the total area. Okay? So current density is I over A. Because it's uniform, you get the same result if you just consider the section you're enclosing or the entire thing. Okay? That's the logic. And the reason we want that is because we can solve for I enclosed. I enclosed is I total times the area we're enclosing divided by area total. Okay? I total, we're just calling that I. What's the area we're enclosing?
Fire square.
Big R.
Pi little r squared is what we're enclosing, right? We're enclosing just this one, okay? What's the total? That's pi big R squared. That's the total area that the current is going through, okay? So this is basically telling us what fraction of the total current are we enclosing. It's basically the total current times little r squared divided by big R squared, okay? Good so far? Next, we're going to do integral of b dot dl equals mu naught times I enclosed. In other words, we're going to apply Ampere's law because we have both sides of the equation now. We have the I enclosed part, we have the b dot dl part. All we're doing is putting it together, okay? So for the b dot dl part, we have b times 2 pi r equals mu naught times I little r squared over big R squared, which means b is equal to this. Just divide out the 2 pi r. On top, you have mu naught times I times little r. On the bottom, you have 2 pi times big R squared. Now again, this applies for little r less than big R. That's when we're inside of the wire. That's what we get. So notice what this is telling us. If little r is equal to 0, that means we're calculating the B field at the center of the wire. What do we get? It's 0, right? There's 0 B field right in the middle. And then it gets stronger and stronger as you go up. That's at least true as long as we're inside the wire, okay? So to summarize here, let's just go to the slide. Inside the wire, the B field is mu naught times I times little r divided by 2 pi times big R squared, okay? Now let's do a different Amperian loop. This one has the same kind of geometry to it, but it's fully outside of the wire, okay? So that's loop number 2. The radius of this loop, which again we're calling little r, is bigger than the radius of the wire, which we're calling big R. All right, can someone tell me how much current are we enclosing in this case? We're enclosing the entire current, because we're not just partially enclosing the current in the wire, we're enclosing the entire thing, the whole thing. So that actually means this is a very simple case to knock out, because so now we have our Amperian loop outside of the wire, which means we're enclosing the entire current, okay? We could go ahead and work out this integral b dot dl once again, but we would just get the same result as before, okay? We would just get b times 2 pi r, okay? So therefore, we're actually ready to put it all together in Ampere's law. We have b dot dl integrated over our loop equals mu naught times the current we're enclosing. So that gives us b times 2 pi r equals mu naught times I, which gives us b equals mu naught times I divided by 2 pi r, just like that, okay? That should look familiar, right? That's the same result we got for just an infinitely thin wire, okay? So regardless of what's going on inside the wire, the current density is uniform, non-uniform. As long as you're outside the wire, the fields always look the same. They're always given by mu naught I divided by 2 pi, okay? Any questions on that? Okay, so let's summarize. To summarize, when we applied the, that's not it. When we applied this to the second Amperian loop, number 2, we got this, mu naught I divided by 2 pi over 1. Okay? So now you know how to do that problem hopefully this is helping you see how you do other types of problems. Maybe, I don't know, it's like a hollowed out wire with a little, cavity in the middle, right? You'd be able to handle that sort of situation. So let's actually look at this on a plot, okay? You've got your wire, and we can plot what the B field is as a function of distance from the center of that wire, okay? Because we have these two different results, we have to look at the graph in two pieces. So the first part of the graph, for small radii inside the wire, what's the dependence on little r? Because all this other stuff is constant, little r's are variable. It's just a linear relationship, right? We just have r to the first power. So you should just see a straight line going from 0 up to some kind of maximum value as long as we're inside the wire. B field is increasing linearly with distance, okay? As soon as we get outside the wire, now it's a 1 over r relationship. So that looks like this. It's a 1 over r type curve, showing us how the B field is falling off as you get further and further away from the wire, okay? That's what we have. Questions? All right, so we're going to end with one calculation. Take those results and apply it to this situation. Let's say we have a long straight copper wire with a diameter of 2.1 millimeters. Let's say that it carries a uniform current density of 6.75 times 10 to the 5 amps per meter. Question for you is, what is the magnetic field 0.5 millimeters from the center? And what is the magnetic field 4.5 millimeters from the center? So in the first question, we're inside the wire. In the second question, we're outside, okay? We have the formulas that go into this, and the mu naught constant values given here. So you should be able to work it out, okay? Take a few minutes to work that out. The first step, of course, is you're going to have to find what the current is, given the current density. Okay, I realize we're a little bit pressed for time, so I'm gonna kind of change plans and we'll just go through this on paper because I don't think there's enough time. So let's work this out. Let's start by finding the total current, okay? That's what we need to do first. We need to do this in order to use our formulas. So remember, I is the same as J times A, right? It's your current density times your area. Because J is just I over A, I is J times A, okay? Our total area is pi times big R squared, right? So if we multiply the current density times the total area, we get the total current. So let's put the numbers in. We have, for J, we have 6.75 10 to the 5 amps per square meter. That means when we do pi r squared, the radius should be given in meters. the diameter of this wire is 2.1 millimeters, so the radius is a half of that. It's a half times 2.1. 10 to the minus 3 puts it in meters, okay? So we'll square that, and that would be the calculation. What are we getting for the total current right here?
It's 4.67 times 10 to the 4.
Did you square it?
Yeah. By 2 pi. I did 2 pi watch.
What do we get? Come on.
Two 2.33 times 10 to the 4.
It's just 2.33. Period. Yeah. Okay. So yeah, about 2 amps, a little over 2 amps. That's what you should get. Okay. All right. So first question is, what is the B field at a distance of 0.5 millimeters from the center? This is inside the wire, which means we're going to have to use this expression, which is U naught I times little r divided by 2 pi times big R squared. So here, let's put the numbers in. We have 4 pi, 10 to the minus 7, TMA. I is 2.338 amperes. And our radius is 0.5, 10 to the minus 3 meters. Okay? That's how far from the center we are. Okay, divide that by 2 pi times the radius of our wire squared, which is 1/2 times 2.1 times 10 to the minus 3 meters, square that. So what are we getting for the B field? This is like 2.1, 10 to the minus 4 Tesla. Okay. Do we agree? All right, let's do the last one. If the radius is 4.5 millimeters, now we're outside of the wire, which means we're going to use this expression. B equals mu naught times I divided by 2 pi times little r. So we put the numbers in, and we have 4 pi, 10 to the minus 7, TMA times the current, 2.338, divided by 2 pi times this distance, which is 4.5, 10 to the minus 3 meters, right? What do we get for this? Uh, 1.04, 10 to the minus 4 Tesla. So this is pretty typical of what you'll find in, normal wiring and normal appliances that you find in your household. Okay, so magnetic fields aren't all that strong. That's it for today. We'll keep going with this on Monday next week. Okay?